Good afternoon, everyone. Thank you for attending this session. Really appreciate it. I realize you have choices, 5 other choices, but you decided to attend this session. And so thank you for that. Before I get started, just curious to get a show of hand, how many people love dynamic programming problems? Okay, it's like less than 5 people raise their hand. So is it safe to assume that a lot of you are finding dynamic programming problems challenging, to say the least? Yeah, okay. How many of you are actually interviewing? Just curious. All right. Typically, I don't see a whole lot of dynamic programming problems being asked during the interview. So this is more like for learning how to solve it and apply this to similar problems. It's a fun dynamic program, fun programming technique to learn. So the goal of this session is to provide you a few tips, and hopefully that will help you get better at handling DP problems. Obviously, it takes more than 45 minutes to master dynamic programming. But hopefully, by learning a few tips, you'll be on your way to get better, and hopefully you spend more time playing around with it and become a master at it. So 6 months ago, I was not that good at solving dynamic programming problems, and I said, I want to get better at this. And one of the principles I use for learning something new topics is to teach this to someone else. So that's what I'm doing now. And therefore, it forced me to spend a lot of time learning about DP in the last 6 months. So I hope that you can apply the same principle for you in the future. If you want to get better at something, the best way is to teach someone else. And that's a great forcing function for you to learn. And hopefully next year, you'll be up here teaching some other topics that you want to learn more about. All right, with that, I'm going to go and this is the agenda. Quick overview of what DP is, and then we talk about some of the characteristics of it, and then the approaches, commonly approaches being used out there, and then talk about the recipe. I think that is kind of the key to solving DP problem, the recipe. And then I'll highlight some of the tips. I watch a lot of videos online, and they teach you how to do DPP, but the problem is they always jump into the code, right? They walk you through the code and say, hey, this is the code and how this is that, but they seldom tell you how to come up with a solution. And that's what I'm trying to figure out while studying this, and I'll share a few tips. And then we will walk through maybe, I think, 3 or 4, 5 problems, depending on time. And then feel free to ask any questions along the way. Okay, so it's a problem-solving technique for optimization problem. Not always, most of the time. And when you do optimization, you often have to deal with exploring all possibilities. And that's where combinatorial comes in. And that's the part that really creates a lot of challenges for us, at least for me. It's like when you get exposed to too many ways, then your mind starts to go, okay, how do I solve that, right? Also note, when a DP problem is given to you, it often comes with a set of constraints. Sometimes that's explicit, sometimes that's implicit. And that's also creating another challenge for you. You have to figure out what are those implicit constraints are. It's both a mathematical optimization method and computer programming method. The more I learn about this, the more this becomes true. There's a mathematical aspect to solving this kind of problem. And you got to be comfortable with that. If you don't like math, you're going to be having a hard time with DP problems. And then once you come up with that mathematical formula, you have to translate that to code. And that's the second aspect of this. It's a computer programming method. And you probably have seen or learned that oftentimes solving DP problems becomes repeated and smart recursion, right? Plus memorization. I'll talk about that as well. And the ability to visualize the recursion tree in your mind is extremely helpful to solving DP problems and also analyzing the runtimes and whatnot. All right, challenges. Right? I'm talking about exploring possibilities. That's when our mind becomes really bogged down. Oh my God, too many approaches. What do I do? They're not really intuitive and requires you to have strong problem analysis. Really think through what are the options that you have. Think back about the first principle of solving some problems and reasons from there. Okay? How do you identify DP problems? Oftentimes is optimization, right? Largest, smallest, minimum, biggest, smallest. But not always, but most of the time they are. And then you have to make choices. That's one of the key things about DP is there are choices you have to make. And you have to figure out what are those choices, and then which choice will give you the best optimal solution. Guys. Right, so what are the different characteristics of DP problems? You've probably seen these and read it many places. They call optimal structure and overlapping subproblems. If you're not, you should try to really learn about these, and I'm going to quickly go through them. Optimal structure is pretty simple. It's essentially the solution of a given problem can be obtained by using optimal solution of its subproblems. I underline and bold and store the keyword there, subproblems. That's another way people describe DP is you got to come up with subproblems. They constantly say that, but they don't tell you how to come up with those subproblems. But it's one of the key things. So let's take a look. Right, you take a problem, you somehow break it down to subproblems, and those subproblems are discrete. They're independent. They don't depend on each other. And this lends itself to recursion. Right? I call this the manager approach. Right? If I have a problem, if I have a director, I have a problem, I get my lieutenants together and say, hey, you solve this problem A, you solve this problem B, you solve problem C. And then come back to me, and I'll take those three solutions and I combine it to solve my final problems. And then my lieutenant will do the same thing to his people. So that's the optimal structure. So an example, if you have an array of numbers and you want to find what's the minimum value, right? You probably think you're going to iterate from beginning to end and find a min, which is fine. The other way of thinking is breaking into subproblems. I split it in half again, and I find the min for each one of those, and then I combine it to find the min. Right? So it's a different way of solving the problem, but using this subproblem approach. And if you're familiar with Fibonacci formula, it's the same thing, right? By solving fifth of 5, it's essentially a combination of fifth of 4 and 3 subproblems, optimal substructure. The final solution comes from the optimal solution of subproblems. Okay? So that's the first one. The first one is the overlapping subproblems. Very simple. It sounds very fancy, but all it is the same subproblems appear multiple times. And this is a very important characteristic here. If a problem doesn't have this characteristic, then DP is not the right solution for it. Okay? And if you look at the picture again, if you break the problem down to subproblems, and you start to see the same subproblems appears multiple times, right? And not all subproblems appear exactly the same number of times, right? That's not always the case. So this is a very important characteristic here. And this is where DP helps, because if you have same subproblems, so then why solve them multiple times? You solve them once, and then you save the result. So therefore, you can reuse it. So that's what I call memorization. Okay? And by the way, there's a difference between memorization and memorization. Does anyone know what the difference is? Memorization is about memorize something ahead of time, right? Memorization is memorize things you just computed right there and right then. So you can reuse it. So there's a slight difference. So let's talk about a problem that doesn't have the overlapping subproblem, which is merge sort. That some of you might have remembered. Right? Merge sort, you split in half, and then you merge them. Those subproblems, as you can see, they're not overlapping. So therefore, DP is not the right solution for this kind of problem. Unlike merge sort, if you take Fibonacci, then you're starting to see this, right? When you draw it out in a tree, you see that fib of 2 appears twice, fib of 1 appears twice, and so on. So therefore, if you compute fib of 2 once and you save it, therefore the runtime will dramatically reduce. Okay? Does that make sense? Overlapping subproblems, optimal substructure, those two things. Approaches to solving them. You probably have read about this. There's top-down and bottom-up. And if you first learning about this, it's very confusing. What the heck does that mean? Right? I'm going to talk mostly about top-down because if you're going to solve the dynamic programming problem on an interview scenario, you more likely just apply the top-down and then optimize it, and then you're pretty much done. You don't have to worry about the bottom-up. So bottom-up, top-down is pretty straightforward. You start from the top. You say, I want to figure out a solution for fib of 4, but I don't know what it is yet. But that's what I want to figure out. So now I'm going to figure out I'm going to go and find a solution for the subproblem of fib of 4. Once I have those, and I can combine them, right? Then it's just going to go top and go down to the bottom where it reaches the base case, essentially. So that's the approach of top-down. And usually it's recursion. Top-down is you can kind of associate the two together. Recursion, because the problem gets smaller and smaller and smaller until it reaches the base case. There's a joke out there that, how do you explain recursion to a 4-year-old kid? Using the recursion approach, you're going to explain it to the person that's 1 year younger than you are. And that person is going to explain to the next person that's 1 year younger until you reach the base case of someone's 4 years old. I just learned that 30 minutes ago. So that's top-down approach, okay? And then the bottom up is you want to solve fib of 4, Fibonacci of 4. So you're going to solve from fib to 0, 1, 2, 3, and then go up to 4. So that's what I call bottom up, right? From the bottom all the way to the top. And oftentimes, and this is using iteration, while loop, for example, to do this kind of thing. The downside is you might solve subproblems that might not be necessary to solve the final solution. So you might have to do some extra computation. Unlike top-down, you always solve exactly the needed subproblem to get to the final solution. Okay, so one of the courses that I watch is the MIT Introduction to Algorithms, and in their dynamic programming section, the professor outlined these 5 steps, right? Define subproblems. The part that, you see the part I put a red line underneath? Guess. What the heck? You solving a problem, you guess? And it turns out it's very true. It's a different way of thinking, and I'll show you that in a second. So you guess of it, and then you guess part of it, and then you come up with the recurrence, and that's very important as well. So those are the steps from that course. This is the steps that I kind of combined from a bunch of other places that I learned from. First is the top-down approach. And the top-down approach consists of 2 things. Coming up with the top-down approach, and then apply it. Once you have that, then you analyze the runtime, and space. And then from that, you apply memorization on it to optimize it, right? And then after that, if we want to convert to bottom up, you can. But the top 3 steps are, as you see, I put an icon important. That's the most important steps of solving DP problems. I think the point is to the runtime is essentially going to be very similar between top-down approach once you apply memorization. The difference is some cases people don't want to do recursion, right? Recursion has a limitation in terms of stack, the amount of recursion, the depth of the recursion. You might run out of stack trace or whatever they call it. So by doing bottom up using for loop iteration, you don't have that kind of problem. If the depth of your tree is huge, that's when you use bottom up. Okay. All right, so this is the general steps, and then I'm going to focus a lot on the top-down approach part of it. Yeah. Yeah, but when you do recursion, anytime you do recursion, right? If the recursion tree is huge, you tend to run that kind of problem. But true, yeah. I mean, you can do. That's true. All right. So what does top-down approach looks like in terms of code-wise? So in this example, we're not focusing on how to come up with a top-down approach. This is about applying it once you know what the solution is. So Fibonacci, I think most people are familiar with that, right? It's the solution that is given to you, that formula. Applying it is translating to code using recursion. It turns out it's very, very simple because you just essentially translate that formula to that line of code, right? Very direct. The only thing you have to add to it is just handling the base case in this example, right? So the beauty of recursion, but also that's where the challenges comes in. This recursion tree is expanding, and then you need to be able to visualize it. And the best way to visualize it is to draw it out, okay? And it helps tremendously if you draw it out. You don't have to draw the entire tree. You draw enough of it so you can mentally understand it. So as you can see, you got fib of 4, and it's split, right? The branching factor is 2, right? Because of n minus 1 and n minus 2. So that you see the tree expanding. Okay. Now you might remember from the old days learning trees in school. What is the complexity of this? Right? It's the branching factor and the depth at the tree. That's what your complexity is. So in this case, we branch 2 times, and the depth is, in this case, it's n because each time we minus by 1, essentially get down to 0. That's your base case. So the runtime is going to be your 2, right, exponential. And the space is O of n because that's the recursion stack, recursion tree. When it gets down to 0, then it's going to pop up, right? So that's the depth of that recursion. So that's essentially the space that you need for your program. So we talk about overlapping, right? So that means that if we can compute the fib of 2 and 1 and 0 and then save that, and therefore it will dramatically reduce the runtime. And applying memorization is quite straightforward. Your function will take an additional parameter. We'll call it cache or whatever that is. It could be an array, it could be in a hash map, whatever that is for you to look up based on a certain key to give you the result. So once you have that cache, you only have to add 2 things. At the beginning, look it up if it exists. If it exists, returns it. If we have a solution for that, return it. If we don't, go ahead and do what we normally do in the middle. But before we return, we save the result in the cache. Right? Very simple approach there. Look it up. If it exists, return. If not, save it before return at the end. So that's essentially memorization. Does that make sense? Okay. So if you look at that, if we do memorization, then the only nodes that we have to solve for are the one in blues. So now what is the complexity? It becomes O of n now, instead of n2 to the n. Okay, so that's the power of dynamic programming using memorization. It's all about trading space to speed up the runtime. Okay, and then coming up, in terms of turning up, convert to bottom up, then it's essentially that you using iteration, and we have a cache, an array of this time, and then we just build it up from 0 to n, or 1 or 2 to n rather, because we know the base case of 0 and 1 already. So we're going to go from 2 to the n, and then build a cache up. And then finally return the cache of n at the end. Okay, so that's an example of how to apply DP to Fibonacci. Now, what we didn't talk about was how did they come up with that formula, right? Because if you're able to come up with that formula, you're 75% there of solving that problem. So let's talk about how to do that. So that's what I call coming up with a top-down approach. The first thing is you should try to come up with a brute force solution. Don't worry about optimization at this point. Okay? Just come up with a brute force approach. While doing that, observe the set of choices or constraints that's given to you or implicit inside the problem statement. If it's given to you, then it's very straightforward. If it's not, then we got to spend more time figuring that out. Okay. The kind of choices you have to make is typically based on the constraints that's given in the problem statement. And the third one is related to the previous slide that I highlight with the red line. Assume that it's already a solution. Let there be a function that can solve some problem for you. And then how do you leverage that? Okay. This will make a lot more sense when we go through an example. And then from that, you can figure out the final solution by asking this question. What would it take to solve when you add n, element n, or whatever that is? Okay. Once you're able to do that, then you can now establish the recurrence, the mathematical formula, right? And then from that, the sub-problems will emerge. Because when looking at the formula, it becomes a little bit obvious. So once you have that, the next step is to visualize it, right? And then analyze the runtime and so on. So these are the steps. Try to come up with brute force. Don't think about performance optimization at this point, because we'll come back on how to apply memorization to optimize it. All right? So let's see how do we apply this to this simple problem, one of the classic DP problems. How many of you have seen this problem before? All right, only a few of you, okay. So the problem says, given a row of coins, which can have duplicates, and our goal is to pick the maximum amount of money from this row of coins. Okay? So you see the word maximums, okay, hey, that's an optimization problem. The constraint that's given is no two coins adjacent can be picked up together. Okay, so here's an example of 5, 6 coins, and then we can kind of scan through this and say, hey, if I try 5, 2, 6, right, I cannot, if I pick 5, I cannot pick 1, right? So therefore, I can pick 2. So I pick 5, 2, 6, that sums up 13. If I try 1, 9, 2, that's 12. But if I pick 5, 9, and 2, that's larger. So, it's a small array. You can scan through it and kind of do the computation in your mind, right? But then you say, okay, how do I come up with a solution for this? Also, what if I give you a much longer array? Can you come up with that solution? Can you scan through it? No, it's not. It's impossible, right? So you have to use another approach. So here's the first step. Well, I kind of jump ahead, but let's assume this is what we want to solve for. Maximum value given n. N in this case is the index, the last index of the array. Right? We have to scan from beginning to end. We have to go from beginning to end of that corner rows. When we get to the last element in that array, hopefully we have the maximum amount of money. Okay? So that's the function that we want to solve for. MV of n. N is the index. Okay? So let's revisit the problem. The constraint says no two coins adjacent can be picked up together. Now I talk about the guessing part, right? Assuming that we have the maximum value, we had the index number 5. Assume that we have the solution from 0 to 4, the maximum value for each of the indexes from 0 to 4. Assume we have that. Don't care how we do that. Assume that the solution exists. How can we solve for MV of 5? Okay, remember the choices that I was talking about? At this point, we have to figure it out, okay, I know the solution from MV of 0 to 4. I'm at MV 5. What are my choices? The choices come from the constraints that's given to us. It says no two coins adjacent can be picked up together. So I got 2 choices, right? What are my 2 choices? Exactly. So that's the choices that we have. And from those 2 choices, we take the max of it. Right? So we have MV5, we have 2 choices. Either pick up that coin and add the max at 3. The coin not adjacent to it. Or we use the maximum value at the coin at 4. Those are our 2 choices. And we pick the max out of that when we're MV5. So now we know the solution to MV5. How do we make it generic? How do we make it general? It becomes this recurrence formula. Right? I literally just take n and replace 5. That's it. So you have MV minus 1, comma. The other option is MV minus 2 plus the value of the coin of n. That's it. That's your recurrence formula. So the next step is now you have to think about the base case, right? Because the recursion is going to end somewhere. So your base case is when you get to the 0, right? And the value is just the coin, the value of that coin at the 0 index. So you see what I just went through in terms of how I come up with a solution? I'm assuming I have a solution from M0 to M4. I don't know how. If I have those, how do I solve the MV5? And the way I solve that is by asking what are the choices that I have at that step. Now, in this case, the constraints given to us, the choices are explicit. Okay, so it's easy. So now we know that, so now we got to ask about these things. What are the subproblems? What's the optimal substructure looks like? We kind of know what it is, right? Because from the MVN, we know what the subproblems are. Can you spot the subproblems? Right? The MV n minus 1, MV n minus 2, those are subproblems. Are they overlapping? Maybe. What if you draw it out? So you start drawing it out like this, right? It branches two ways. Does this look similar to Fibonacci? Right? And then therefore the runtime is exponential. And then now we take that recurrence formula and translate to code. As you can see, it's very similar to Fibonacci. We just have to add the base cases. That's the one thing about recursion, right? You can express it in a few lines of code. So if we look at the tree, we realize there's a lot of overlapping problem, very similar to Fibonacci. So therefore, we just apply memoization to it, right? It's the same couple lines of code, similar to Fibonacci. And then we do that, now the runtime is O of n. So this is a variation of Fibonacci, but we just went through an exercise of how to come up with a solution. And then if you want to convert the bottom up, then it's very similar to Fibonacci as well. So you build from 0, MV of 0 to MV of n, filling up that table as you go. So I won't spend too much time on that. Okay, now let's go to a slightly different problem. Still about coins. So we have this machine that can make change. Okay, you give it a certain amount of dollar, it gives you back a bunch of coins. The only denominations that it has or can support is 1 cent, 6 cents, and 10 cents. And it just so happens that it has infinite number of coins per denomination. Okay, so the problem is given amount of n dollars, we want it to return the fewest number of coins. The first problem was about max. This is fewest, right? Still an optimization problem. The first thing you should do in any problem is try out a few examples, right? So you say, okay, if I give 1, how many coins do you think I'll get? I give 7, how many coins do you think I get? And if you start applying greedy approach, you could, right? You say, I'm going to start with the largest coin and then go from there. But it turns out for 12, if you apply the greedy approach, it's going to fail. Right? It's going to give you back 3 coins. But using DP is going to give you 2 coins. Okay. Now, obviously, if you give a small number, the amount was small, then you can kind of work in your head, right? In terms of how many coins. But when you say 753, it's hard to count what number of coins, right? All right, so now we're going to see if we can apply the same steps that we went through. Let's say we want to solve for DSP 21. That's our amount. And we're going to do the same thing. We're going to assume we have solution to DSP from 0 to DSP 20. How do we solve for DSP 21? Right, the next question you ask is, what are my choices? What are my constraints? In this case, what are our choices? Exactly. And in this case, you want the fewest number of coins, right? So it's going to turn out something like this. For all the coins that I have, I'm at 21. I'm going to explore all options for all the coins, for each one of them. Because I already have solution from 0 to 20, right? So if I take 21 minus 1, that's the first coin. Then it essentially solving for DISP 20, which I assume I already have. I do that for all the coins. Which one of those is going to give me a number? I'm going to take the min out of those choices and add 1 to it. You see how that works? All right, so now you're getting the hang of this thing, right? Then the next question is, like, what are the subproblems? Is there an optimal substructure? Wait, we haven't talked about how to convert that to a general formula, right? That was for a very specific DISP 21. How do we make it general? It's essentially 1 plus min of DISP of n minus d of j, meaning all the coins. You iterate to all the coins, and you calculate the minimum of the n minus that coin. Right? That's, in this case, we're going to iterate to all the denominations. Then you have the base case there. And then you're going to ask the same problem questions again. What are subproblems? Is there optimal substructure? Are they overlapping? Again, drawing out your tree. It's very important to draw this out. Because the moment you draw it out, things become fairly obvious, right? So you take DISP 21, you draw it out. In this case, you have 3 coins. So you got DISP 20, 15, and 11. And you keep doing that again, and you're starting to see this tree, and you're starting to see overlapping subproblems. It might not be obvious at first for this problem, but you see it. What's our runtime? There's 2 things you want to ask. What's your branching factor? And what's the depth of the tree? In this case, the branching factor is 3, the number of coins. The depth of the tree is what? Right, because we have a coin of 1, so it's always go by 1, right? Smaller by 1, so it's going to eventually go down. The maximum is go down to 1 by 1 and go down to 0. So the depth of the tree is going to be n, or 21 in this example. So by translating that formula that we have here into code, it will look something a little bit different than the Fibonacci, because we have to iterate to the coins, right? That we didn't do before in the Fibonacci case, or the coin change. So here we iterate to all the coins, and we calculate the min coins for each one of those. And then I have a count at the top. It's the global min count, and then update that as we go through the loop. And finally, we return the count. As you see, it translates to only like a handful of lines for codes. So the runtime is coins to the amount, right? The branching factor to the depth of the tree. And the space is the depth of the tree, which is the amount. And then we apply memorization. It's the same approach. No difference here. Right? Before we do computation, we look it up. And then we save it at the end, and that's it. And that's how we get rid of those overlapping subproblems and reduce the runtime to O of n. Well, in this case, it's not O of n, right? It's something different. The bottom-up approach is similar as well, because now you're going to build from DISP 0 to DISP 21. Okay? And using iteration, so we have like a cache, and then we have a for loop, right? And then fill it up from the bottom up. Okay, so a different problem, a slightly different problem, still related to coins. So far we do max and min. This problem is not about max and min. So we have denominations, And again, infinite number of coins for each denominations. Given amount n, compute the number of unique ways of making change. So we're not doing optimization. We're doing counting. But DP is still applicable because there's still subproblems. There's still overlapping subproblems. So it's not always about optimization. This gets a little bit more challenging now. All right? Like any other problems, the first thing you do is you kind of go through an example, right, to get a gist of it. So if NW is 5, then in this example, we have 4 ways of making change for 5. One way is to all ones. Second way is 2 and 1. The coins 2 and 1s. And then the last one is the coin of 5. Right? So we're using all the coins, but not all together at the same time. Not necessary. So now we're going through the same step again to see if that helps us, right? Given amount of n, we have a set of denominations. If we know the NW falls from 0 to 4, would that help us? Would that help us solving NW of 5? Well, in this case, we're trying to find a number of unique ways of making change, right? Unique ways of making changes. We're not doing minimum or maximum anymore. So we're not like iterating through sets of choices. There's still sets of choices we have to make. Does that work? Let's say we have NW4. What does that look like? Well, how many ways? It doesn't quite work that way if you try out a few examples. So there has to be another way. There has to be a different way than what we've been applying. And this is another pattern. Anytime you, I guess you know about building subsequences. Another pattern in when you do combinatorial kind of thing is include or not include pattern. Okay, this is a very handy technique to remember. So what that means is for each of the coins, we have a choice to include or not include in our way of figuring out a number of unique ways to make change. So what translates to is if I'm at NW5 and I got 3 coins, I have 2 ways of counting. One is with the coin of 1 or without the coin of 1. So choose or not choose. And then the combination of that is how many ways I can count. You make change for 5. Right? So essentially what I'm doing is I'm generating almost like all the subsequences of the coins and see if I can make a change out of 5 from that. So that translates to this formula of NW amount minus coin with the same set of, I'm using 1, so they're including that, plus without that coin of 1. So it gets more complex, right? For all the coins, I would do that. So the way to translate this to code requires a little bit more, meaning that I need to have an index to point to what the coins that I'm referring to. So you can start with the index of 0, meaning the first coin. So I got 2 ways of counting coins, right? Including that coin at index 0 or excluding that coin. Excluding that coin by bumping up the index by 1. And then now I just combine those two. And that's my total number of ways of counting coins. Let's look at the tree, right? The left-hand side, or your left, is include, and the right side is not include. So you can keep doing that, and then you can also see the tree as well as overlapping subproblems. In this example, not a whole lot, but there's some. Okay? So this is a slightly different problem than the previous two that we worked through. So, but the approach is very, very similar, right? So now applying memorization, it's the same technique, but now we got two dimensions that we're going to think about: the amount, and then the coin that you are including or not including. So now you need two-dimensional array to manage that for you. But the approach is the same, right? Look it up is there. Once the computation is done, save it before you return. And then bottom up is very similar. You're going to apply the same thing. So, okay, the next problem is quite interesting, and then I'll tell you why. Longest increasing subsequence. Okay, given an array of unsorted integer, if it's sorted, then it doesn't make sense, right? Unsorted, find the longest increasing subsequence. Subsequent sequence means the elements are not contiguous. Okay. And like in this example, we got 3, 2, 6, 4, 5, 1. There are many increasing subsequences in here, but we just want the length of the longest one, right? So the answer is 3. There's like 2, 4, and 5. They're increasing from left to right. Another would be 3, 4, and 5. That's another subsequence with the same length. So if you're not familiar with subsequence, you should definitely go and learn and study that because it's fundamental to computer science. You need to know how many subsequences are there in an array of n elements. How many people know that? 1. All right, not many people. So you should go learn that. It's just a fact. It's just a very simple concept, right? There's 2 to the n subsequences in an array of n. That's it. So one way of solving this could be just compute all the subsequences and find out which one have increasing, all increasing element. And among those, which one has the largest length? That's one way. But as you can see, it's 2 to the n, right? Now, if I give you a longer array, then it's going to be more challenging to figure it out. You can't just scan anymore, right? So how do we solve this problem? Then again, we have a function that we solve for. N is essentially the last element in the array. Same approach. If we add 3, assuming there's a function that will give us the answer from 0 to 2, and we add 3, is that useful to us? And if it is, what are our choices? And I will give you a hint. The choices are not explicit in this problem. So this is an example where the choices, the constraints are implicit. It's inside the problem itself, but not given to us explicitly. What are our choices? But true, that is true. But our goal is to come up with that formula. So how can that help coming up with a formula? What are our choices? That's one thing to think about. When we were 3, the choices we have is we have to iterate all the way to 0. Right? We know from LIS of 0 to LIS of 2. We know the longest increasing subsequence for each one of those. We're going to do max of something, that's correct. Say that again? Well, it's not sorted though. This is an unsorted array. I'm not sure I follow you. That's the choices that we have. And we can't just go back by 1. We have to go back all the way to 0. So that's what we have to do. We have to go back from 2, go back to 1, go back to 0, with the constraint that the value at C of 3 is greater than the value at 2 or 1 or 0. Only then we can extend that sequence. Right? So in this case, like I said, the choices that we have are implicit inside a problem. And we have to figure that out in order to solve this problem. But the choices are there that we have to make. So now that we have this formula, how do we make it more general? It's essentially a little bit similar to the previous problem. It's the max of all the LIS from j from 0 to n minus 1, or n to 0, n minus 1 to 0. With a constraint that the value of at C of n is greater than C of j. Right? So when we're at n, we have to go all the way back. And our base case is LS0 is 1. Again, so if you draw out this tree, at LS4, you see you go to LS3, LS2, LS1, and 0, and so on. So you see this tree, right? And you see subproblems. And you see overlapping subproblems. Okay, so if we translate this to code, it'll be a little bit similar to the other one. We have the iterate total index of 0 to IDX. We at IDX, we iterate from 0 to IDX. And we calculate the LIS for each one of those. And then we take the max out of that. In this case, we only want to find the global max. So I have a variable called global max, and then update that as I go. Okay? So based on this, what's our runtime? It's not as simple as before. For each n that we have, iterate all the way back, right? We're at 0, all the way to 0, 1, 0, 2, and then go back to 1 and 0, 3, go back to 2, 1 and 0, 4, we got 3, 2, 1. We do that n times. So it's n squared, right? It's n squared. And the same thing, right? These are overlapping subproblems. So we compute them and then put it in a cache, and we can look it up, and then we return them. And then we drop it down to open. You see the pattern? Bottom up, same thing. We're going to start from 0 and build it up, right? So the opposite. Instead of top down, bottom up, start from 0 to n. All right, the last one is an interesting one here. Longest palindrome sequence. Most people know what palindrome is, right? It's a word that you can read backward, forward is exactly the same. Like civic. The word civic is a palindrome, right? So given a string, which is a sequence of letters, find the longest palindrome subsequence from that sequence of letters. That's the question. Notice there's no constraints at all that's given to us. But it's implicit, it's in there. We just have to explore it. In this example, the palindrome is subsequence is that word, and the length is 5. So the answer is 5. Right? It should return 5. What about this one? It's more challenging, isn't it? You can figure it out, but you're gonna spend some time to go through it. But the answer is 7 characters. That's a hint. And it's here. Okay, so that's the problem that we have to solve. Given a sequence of letters, find the longest palindrome subsequence. Okay, a brute force, it might not be the DP way, is generating all the subsequences, right? The same thing of the previous problem. Generate all subsequences. For each one of those, figure out which one's palindrome. Right? That's one approach. That is, what's the runtime of that? How many subsequences are there in an array of n characters? 2 to the n. 2 to the n, right? 2 to the n. All right, now let's apply our steps. This is a shorter word. We want to figure out a palindrome word in here. What are our choices? How do you figure out a word's palindrome? Well, if it is a word, but I'm just saying, how do you find within the sequence of characters? Well, we have to compare somehow, right? Compare what with what? Compare E to N, right? Okay, now if we, at this point, what are our choices? You got 2 pointers to different characters. What are the choices? What are the possibilities of those 2 characters? Either they match or don't match, right? Those are the options that we have. So now we got to decide. If they match, what do we do? That's right. If they match, then we add 2, and then we move both pointers in towards each other, right? That's our first option. If they don't match, then what do we do? Then we try all possibilities of that by exploring those 2 choices he's talking about. So if we have LSP of 0 and 5, 2 possibilities if they match. If they match, then you say 2 plus the LSP of 1 and 4. That's the first case that we talk about, right? Or the max of LSP 0 and 4 and LSP of 1 and 5. The two choices that we have. So you see, it's all come down to choices. But the choices are sometimes not explicit. They're implicit. And you have to figure out those choices. Oh, yeah. That's right. Also, I only type L instead of LSP. Yep. Thank you. Okay, so once you have this, you are 75% home. You just have to translate to a more general formula. So we're representing I and J, right? If they match, then 2 plus I plus 1, J minus 1. Oh, I have a same mistake there. Or the max of LSP of I plus 1, comma J, or I plus J minus 1. Yeah. Yep. Again, so now you have this recurrence formula. You can just draw it down a tree. And I was lazy, so I copy from somewhere else. But you think about 0 and 5, right? The case matches, we don't have to think about that too much. When they not match, then become 1, 5, 0, and 4. And you're starting to do the same thing again and again. You get this tree. And you see some overlapping, right? 2 and 4, and so on. So what's our runtime? First question, what's the branching factor? 2, right? What's the depth of the tree? Yeah. So it's 2 to the n. By having answers to those two questions, you can automatically come up with the answer of the runtime. And the space is O of n because, right? Good question. What do we do with that? Should we include that in the computation? Is it necessary to include that? What was that saying? Ready to go home? Time to go home? Are we running overtime? 4:30. Looks like we're running overtime. All right. Does anyone have the answer to this question? How come we're not including the other case where they match? Well, memorization is just the optimization part. But right, we have this formula, but our tree does not consider the when they match. Yeah, does that answer your question? The answer is 2 plus of a smaller problem of L I plus 1 and J minus 1. And it becomes the tree like this too, right? So that's why. All right, so that's all the problems that I have on this slide deck. I hope you find the steps useful. Hopefully you like dynamic programming problems a little bit more than before. By the way, dynamic programming exist in real life. The techniques being used to solve real life problems, right? Some of them are listed here. So in summary, we went the overview. We learned about the characteristics of DP problems. We talked about different approaches, top down, bottom up. We talked about a recipe, coming up with a top down approach, applying it, applying memorization to it to reduce the runtime. And then we went through four or five problems. So thank you for attending this session.